Okay, let's dive into a real cosmic treasure chest in our own backyard. Well, if your backyard stretches tens of thousands of light years anyway. Today, we're unpacking the story of Westerlund 1.
Ah, yes. A fascinating object.
Imagine a stellar city not built over millennia, but kind of popped into existence relatively recently, packed shoulder to shoulder with hundreds of the most massive, most spectacular stars the galaxy can make. That's basically Westerlund 1, right?
Mm,
Arguably the most massive young star cluster we have right here in the Milky Way,
yeah.
first spotted by Bengt Westerlund back in '61.
What's truly fascinating, though, is that for decades, this incredible object was, well, incredibly difficult to study.
Right. Why was that?
There's this thick curtain of interstellar dust and gas between us and Westerlund 1. It absorbs so much of its light that even its brightest stars appear really very faint from Earth. This high extinction, as we call it, really blinded us, made getting precise measurements tough.
Right, it's hidden away. So our mission in this deep dive is to use the source material, which leans heavily on studies analyzing data from the European Space Agency's groundbreaking Gaia mission to understand what we've finally learned about this cluster.
Okay.
We're going to focus on the scientific detective story of pinning down its fundamental properties, its distance, and its age, and how new, incredibly precise data from Gaia has completely challenged and then refined our picture of this fascinating place.
Absolutely. And it's quite a story. We'll uncover some truly exotic celestial creatures living within this cluster, a cosmic zoo, really,
Yeah.
and trace how astronomers use decades of ingenuity and now Gaia's precise vision to lift that dusty veil and piece together its complex history.
Okay, let's start with what astronomers thought they knew about Westerlund 1 before Gaia started delivering its revolutionary data. What were the basics then?
Well, the general consensus placed it at a distance of somewhere between, say, 3 and 4 kiloparsecs,
And a kiloparsec is.
roughly 3,260 light years. So we're talking maybe 10,000 to 13,000 light years away. Pretty far.
Okay.
Its total estimated mass, including the gas and dust still hanging around, was thought to be enormous, around 60,000 times the mass of our sun.
Wow.
But it's incredibly compact, packed into a radius of only about 1 parsec. That's just over 3 light years across.
So imagine squeezing 60,000 suns into a space only a few light years wide. That's dense.
Extremely dense.
Massive and compact. Why is a cluster like this so important to study, even if it's hard to see?
Because it's a prime example of what astronomers call a young massive cluster. These aren't your average open clusters. They are dense, powerful factories of star formation, often described as the fundamental building blocks that make up galaxies.
Right.
They're surprisingly rare here in our Milky Way and our immediate cosmic neighborhood, the local group, but you find them everywhere in galaxies that are crashing into each other or, undergoing intense bursts of starburst galaxies.
So they're windows into these really extreme star-forming environments, and Westerlund 1 is one of the nearest examples we have.
Precisely. That makes it a crucial laboratory. Astronomers are keen to study how stars of different masses are distributed within it. That's the stellar mass function.
Oh.
And how the powerful interactions between these massive evolving stars and the cluster's overall gravity shape its destiny. And of course, as you mentioned, it hosts this incredible collection of exotic stars, which are laboratories in themselves for understanding extreme stellar physics.
Okay, let's talk about that cosmic zoo, because the list of weird and wonderful objects in Westerlund 1 is genuinely spectacular. What kind of rare beasts are living there?
It really is like walking into a stellar freak show. I mean, you find rare, evolved, high-mass stars in numbers you just don't see elsewhere in our galaxy. For starters, there are 4 red supergiants.
Okay, those are the really big, puffy ones at the end of their life, like Betelgeuse, but maybe starting out heavier.
Exactly, but born from much heavier parents, yes. Even rarer are 6 yellow hypergians, incredibly luminous and unstable stars that started life with maybe 20 to 60 times the sun's mass.
60 times.
Yeah. And one star, called W237, is one of the largest known anywhere. Its radius is about 1,200 times that of our sun.
So big enough to swallow Jupiter's orbit easily.
Oh, yeah.
Easily.
Incredible. What else?
Well, you also find 24 Wolf-Rayet stars.
24. Those are the ones shedding their outer layers like crazy, right? With powerful winds.
That's them. Very hot, very massive, very unstable. Then there's a luminous glue variable, another type of unstable massive star prone to violent eruptions. Numerous standard OB supergiants, the sort of workhorse massive stars.
Uh-huh.
And even some truly unusual objects, like a supergiant that might be the product of two stars merging recently. That was suggested a while back.
A merger product. Wow. And the really exotic stuff, you mentioned something earlier.
Yes, perhaps the most surprising find back in 2006 was an anomalous X-ray pulsar CXO J1647 dead of 0.2045P10.
A pulsar, a spinning neutron star. Exactly. The dense remnant of a collapsed massive star. But this one is unusual, and its existence strongly suggests it formed from a progenitor star that must have been incredibly massive, probably more than, say, 40 times the mass of the Sun.
40 solar masses collapsing into a neutron star, not a black hole.
Yeah. Finding that was a significant discovery. It challenges our models of which stars make neutron stars and which make black holes.
So you have all these incredible, massive, evolved stars crammed together. What did this mix tell astronomers initially about how the cluster formed and, importantly, how old it was?
Right. Well, the prevailing idea for a long time was that Westerlund 1 formed in a single, relatively quick burst of star formation.
Like, boom, all at once.
Pretty much, yeah. If that were true, all the stars in the cluster should have been born at roughly the same time, with the same initial chemical composition.
Okay, makes sense. And how did the types of stars present act as a kind of clock for that single burst?
Think of it like, well, looking at population demographics. Massive stars evolve through different stages at predictable rates, depending on their mass.
Right.
Theoretical models show that red supergiants, like those four we mentioned, start appearing in significant numbers around 4 million years after a star formation burst.
Okay, 4 million for red supergiants.
But the population of Wolf-Rayet stars, those 24 energetic ones, tends to peak early and then drops off sharply after about 5 million years.
Ah, I see.
So the fact that you had significant numbers of both types, red supergiants and Wolf-Rayets, initially pointed towards a relatively young single age of around 5 million years for the cluster. That seemed to be the sweet spot.
So the initial picture was single massive burst about 5 million years ago, about 4 kiloparsecs away, tucked behind a lot of dust. Why was it so hard to get past that initial picture and nail things down?
Primarily that dust and distance. Measuring distance directly in astronomy, especially for distant objects hidden behind dust, is really, really tricky.
And previous missions, like Hipparcos, the earlier space astrometry mission, couldn't measure distances this far out, could they?
No, not a chance. Hipparcos was great for nearby stars, but none of Westerlund 1's stars were bright enough in visible light to be observed by it. That heavy extinction just wiped them out for Hipparcos.
Okay, so how did astronomers try to nail down the distance more accurately in decades before Gaia came along?
They used various indirect methods. Some relied on assuming the intrinsic brightness of certain star types, like B supergiants, treating them like standard candles, basically. If you know how bright something should be and you see how faint it appears, you can estimate distance.
Right, but that depends on your assumptions about the star being correct.
Exactly. Others used kinematic distances, trying to estimate distance from how fast the cluster appears to be moving through space relative to gas clouds. Some tried fitting theoretical models to the less evolved stars still on the main sequence, the normal hydrogen burning phase.
And did those methods agree?
They sort of generally converged on that larger distance, around 4 kiloparsecs. So they moved away from Westerlund's very first estimate from 1961, which was much closer, about 1.4 kiloparsecs, based on, much less data back then.
Okay, so by the time Gaia launched, the consensus was roughly 4 kilopc in a young age, around 5 million years, based on those stellar evolution models and the mix of stars. Then comes Gaia, designed to measure star positions and distances with unprecedented precision using parallax. You'd think, okay, problem solved, right?
You'd hope. And Gaia is revolutionary, no doubt about it. But for a distant, dense cluster like Westerlund 1, even the early data, which we call Data Release 2 or DR2, had its own set of challenges.
Like what?
Well, dust still obscures things, even for Gaia in some ways. The cluster is incredibly crowded, making it hard to resolve individual stars perfectly. And for the very precise work needed for distant objects, you have to account for subtle systematic errors in the measurements. Things like a tiny average offset in the parallax values across the whole sky, a 0-point offset. Plus, unresolved binary stars, two stars orbiting each other that Gaia sees as just one blurry point, can also mess with the parallax and proper motion measurements.
So even with Gaia's power, DR2 didn't immediately give a crystal clear answer for Westerlund 1.
Not quite. It set the stage for a bit of a debate, actually.
Okay, so what did the first studies using Gaia DR2 for Westerlund 1 find?
Well, one study by Clark and colleagues in 2019 used the Gaia data mainly to confirm membership for some interesting stars, including some blue stragglers. Those are stars that appear younger than they should, possibly from mergers or interactions.
Right.
Looking at other likely members and trying to account for a potential 0-point offset in the Gaia data, they derived an average parallax for the cluster of about 0.21 to 0.24 milliarc seconds.
A milliarc second. That's a tiny angle, is it?
Wait,
Like
what?
seeing I don't know, a human hair from miles away.
Something like that, yeah. An incredibly small apparent shift in the star's position as the Earth orbits the Sun. And remember, a smaller parallax angle means a greater distance.
So they're 0.21 to 0.24 milliarc seconds translated to.
Roughly 4 to 4.8 kiloparsecs, which they noted was pretty consistent with that pre-Gaia consensus figure around 4 kpc, so kind of confirming the old picture.
Okay, so one DR2 study supported the older distance. But wasn't there another notable paper that got a very different result from the same data?
Yes, absolutely. Aga Kanlu and co-authors in 2020 used a different statistical approach on the DR2 data. They focused purely on separating likely cluster members from foreground or background stars based just on their measured parallaxes using a kind of statistical modeling.
Okay, different method, different result.
Very different. They derived a significantly larger mean parallax for the cluster members, 0.35 milliarc seconds.
And a larger parallax means.
A closer distance.
Right.
Their result put the cluster at a mean distance of only 2.6 kiloparsec.
Well, wait, 2.6 kilopc, that's way closer than 4 to 4.8 kilopc. That's like thousands of light years closer.
Exactly. It was a huge difference. And they immediately pointed out that this had major implications for understanding the cluster.
What kind of implications, if it's closer?
This is where it gets really critical for the physics. If the cluster is only 2.6 QPCs away, the stars we see, given their observed brightness from Earth, would have to be intrinsically much less luminous, less bright in reality than we thought they were, based on the assumption they were at 4 QPC.
Okay. Less luminous means.
It generally means they are less massive than previously estimated for their particular spectral type, their temperature and appearance. And less massive stars evolve much, much slower than very massive ones.
So if they're less massive and evolve slower,
then the cluster would have to be significantly older than that canonical 5 million years to have produced the evolved stars we see, like the red supergiants and Wolf-Rayets. Their findings suggested a much older cluster, potentially even 10 million years or more. This threw a real curveball into the existing understanding. A closer and older cluster.
wow. So DR2 gave us results consistent with the old distance and results suggesting a fundamentally different picture. Closer, less luminous stars, and an older cluster age. What did the third main DR2 study find? Was there a tiebreaker?
Well, Davies and Beezer in 2019 used yet another approach. They selected cluster members based on their proper motion, how they appear to move across the sky together over time, confirmed by prior spectroscopic studies that identified stars with the right chemistry and velocity.
Okay.
Even dealing with the known limitations of DR2 data, their method yielded a distance of 3.87 kilopc.
So basically right back near that 4 kpc mark.
Pretty much, yeah, aligning well with the pre-Gaia picture and also with Clark's DR2 result.
So DR2 was really a mixed bag, wasn't it? Left astronomers still debating. Was Westerlund 1 around 4 kpc and young, fitting the standard models, or was it closer, around 2.6 kpc and older, requiring a rethink of stellar properties?
Exactly. It highlighted the challenges and the importance of understanding the data and the analysis methods.
This brings us to Gaia Early Data Release 3, or EDR3, which came out in December 2020. Was this better data able to settle the score?
EDR3 was definitely a significant improvement. The typical precision of individual parallaxes got about 30% better, and crucially, some of those systematic errors, like the 0-point offset, were better understood and characterized. So the hope was, yes, this would resolve the distance discrepancy.
And did it. Finally nail down the distance.
It moved things strongly towards a consensus, yes. But not without introducing another fascinating puzzle piece related to the age.
Okay. So what happened with the distance first? Did Agakanlu's team stick to their closer distance with the better data?
They did. They repeated their statistical analysis using the improved EDR3 data. Their new result was a mean parallax of 0.34 0.05 milliarc seconds.
So still around 0.34 billion, 0.35 math.
Exactly. Which gave a distance of 2.8 kpc. This was incredibly consistent with their previous DR2 result of 2.6 kpc. So they argued their method was robust, but it was still at variance with the 4 kpc consensus emerging from other studies, and they reiterated the significant implications. lower stellar luminosities, lower turn-off mass, meaning less massive stars were evolving off the main sequence, decreased total stellar mass for the cluster, and an increased age.
Okay, so they stood by their closer distance and older age implication even with EDR3. How about the other side, the ones who favored 4QPC?
Beezer and colleagues also repeated their analysis with EDR3. Remember, their method focused on known spectroscopic members and used proper motions primarily. With the improved EDR3 data, their method yielded a mean parallax of 0.243 lakhs 0.027 milliarc seconds.
0.243 eyes. That's much smaller than 0.34 eyes.
Right, and that smaller parallax translated to a distance of 4.12 kiloparsecs.
So bang on 4QPC again.
Exactly. This result strongly confirmed their previous estimates and brought them back in alignment with the 4KPC picture that most other studies, pre-Gaia and using DR2, like Clark's and their own, had found.
Okay, so with EDR3, two main results were still published. One around 2.8 kPc and one around 4.1 kPc. Though it sounds like more studies were converging on the latter, the 4 kPc distance.
That's fair to say, yes. The weight of evidence from different EDR3 analyses started leaning heavily towards the 4 kPc distance.
Right. Now, where does the twist you mentioned come in? The new puzzle piece related to age.
Okay, so the twist came from that same Beazle paper that found the 4.12 kPc distance. Alongside the EDR3 astrometry, the positions, parallaxes, proper motions, they incorporated new infrared photometry. That's measuring the star's brightness in infrared light.
Why infrared?
Because the coolest, most evolved stars in the cluster, like the red and yellow supergiants, emit most of their light in the infrared. Visible light measurements don't capture their full energy output well.
Got it. So they use new infrared data for these cool giants.
And when they modeled these specific stars using this improved infrared data, comparing them to stellar evolution models, the models were only consistent with a much older age for these particular stars. They estimated around 10.4 million years.
Wait, 10.4 million years. That's more than double the initial 5 million year age estimate that was based on having both Wolf-Rayets and Spurgeons.
Exactly, a huge difference. And it directly conflicted with age estimates derived from other objects within the very same cluster. For example, there's a binary system called W13. Based on the masses and orbital properties of its two massive stars, its age seemed to be less than 5 million years.
Okay, hold on. So now you've got a distance converging around 4 kPc from the parallax data. But stars within that cluster seem to be pointing to two drastically different ages. Some, like the W13 binary, suggesting less than 5 million years, while others, the cool Supergiants, suggesting over 10 million years. How did Beezer et al. Reconcile that apparent contradiction?
Their conclusion was profound, really. They argued that the fact that models assuming a single age for all stars in the cluster could not simultaneously explain all the observed types and their properties. Well, it meant that the founding assumption was likely wrong.
The assumption that they all formed at once.
Precisely. Stellar evolution models based on a single instantaneous burst of star formation simply cannot reproduce the mix of stars seen, especially with these conflicting age indicators. Instead, they proposed that the stars in Westerlund 1 didn't all form at the same moment. They suggested star formation happened over a period lasting several million years.
So instead of one big bang of star formation, it was more like a prolonged, popcorn machine of activity over millions of years. That fundamentally changes our understanding of this cluster's birth.
It really does. It suggests massive clusters might have more extended formation histories than we often assume.
Did independent analyses using EDR3 support this emerging picture of 4 kPc distance and maybe a spread in ages?
Yes. Another important study came from Nagarila and colleagues. They performed an independent analysis also using EDR3 data, but they combined it with spectroscopy of stars in the surrounding field to really refine cluster membership based on proper motions and weed out foreground-background stars.
Okay, an independent check. What distance did their analysis find?
They derived a mean cluster distance of 4.23 kiloparsecs.
Okay, again, very close to the 4.12 kPc from Beezer. Excellent agreement.
Yes, in very good agreement with the 4QPC consensus emerging from Beezer's EDR3 study and others. This independent confirmation using slightly different techniques was really important for building confidence in that distance.
And did they find interesting things about the space around the cluster too? You mentioned foreground stars earlier.
They did. Their analysis mapped the dust extinction in that direction and found a sharp increase around 2.8 kilopc. They attributed this to dark clouds in the Scutum Crux spiral arm of our galaxy lying between us and the cluster.
So that helps explain why it's so obscured and why we see fewer stars beyond it.
Exactly. It confirms there's a significant dust lane there. They also clearly identified a distinct group of stars closer to us, a foreground population at around 2 QAPC distance, which they suggested is likely related to another known open cluster called BH1967.
Interesting.
And importantly, their study of Westerlund 1's structure itself suggested it's not perfectly spherical. It seems somewhat elongated, maybe like a stretched football, and it appears to have a faint, low-density halo of stars extending outwards, particularly towards the northwest, so a more complex shape than just a simple ball of stars.
So Gaia EDR3, after those initial conflicting DR2 results, seems to be really solidifying the distance around 4, maybe 4.1, 4.2 key LPC. And it's giving us a more complex spatial picture and strongly hinting at this prolonged formation history to explain the age discrepancies.
You mentioned binary stars earlier as being valuable checks. How do they fit into this latest picture?
Right. Binary stars are fantastic natural laboratories. If you have a system of two stars orbiting each other and you can measure their orbital motion using spectroscopy, seeing the Doppler shifts as they move towards and away from us, and you can measure their collective movement through space and maybe even their tiny orbital wobble with Gaia astrometry, you can get independent distance estimates for certain types of binaries, eclipsing ones, for example. You can even calculate the stars' masses dynamically without relying on models.
And then that helps with age, right?
Crucially for age, yes. The expected lifetime of the most massive star in a binary system provides a hard upper limit on the age of the cluster, because that star couldn't have evolved past its current state yet if it's still there.
Were there any specific binaries in Westerlund 1 that were particularly useful in this latest phase of the debate?
Yes, the source material mentions several massive eclipsing binaries being studied. One system, W36, was studied in detail by Rocha and colleagues in 2022. Their analysis yielded an independent distance estimate of 4.03980.25 kiloparsecs.
Perfect. Right in line with the 4 kpc EDR3 consensus. Absolutely spot on. And the system W13, which we mentioned earlier, was discussed by Beezer et al. As one of those binaries pointing to a younger age, less than 5 million years. This contrasted sharply with the older ages suggested by the single red supergiants using that infrared data.
So the binaries themselves seem to confirm both the 4 kpc distance and the age spread issue.
Pretty much, yes. They reinforce the overall picture emerging from EDR3.
Okay, so let's try to synthesize these latest findings from EDR3. What's the refined consensus on the distance and age now, based on the most detailed analyses like the one from Navarrete and colleagues in 2022 that you mentioned?
Right. Navarrete et al. Did a very thorough analysis using the full suite of EDR3 data parallax, proper motions, photometry. They started with previously confirmed members and carefully added more likely candidates based on how well their Gaia data matched the cluster's known properties. They ended up with a clean sample of 172 solid cluster members. With this sample, they were able to construct detailed plots, like plotting stars' color against their brightness, a color magnitude diagram, which is a classic tool for understanding stellar populations, distances, and ages.
And what distance did their comprehensive analysis yield?
They derived a distance of 4.06 kiloparsecs with a very small formal uncertainty. This is an excellent agreement, again, with the results from Beezer et al., 4.12 kpc, and Negarilla et al., 4.23 kpc, using EDR3. So the consensus among these detailed independent EDR3 studies has really strongly converged around 4.0 to 4.2 kpc.
And the closer distance suggested initially from DR2.
That closer distance suggested by August and Liu et al. In DR2, though they found it again consistently in their EDR3 reanalysis using their specific method, just doesn't seem to be supported by these other detailed EDR3 studies that look at a broader range of confirmed cluster members and employ different analysis techniques. The weight of evidence is now heavily towards 4 kpc.
Okay, distance settled around 4 kpc. What of the age puzzle? Does Navarrete's work support the idea of a range of formation ages, like Beezer suggested?
Yes, it strongly supports it. When Navarrete et al. Derived ages for the red supergiants in their sample using standard stellar models, they found ages falling in the range of 9.7 to 11.7 million years.
Again, that older age for the supergiants.
Exactly, and this is very consistent with Beezer et al.'s estimates for similar stars like W75, where they got 9.2 to 11.7 million years using the infrared data. However, Navarrete et al. Also noted that the age estimated for that binary system W36, which gave the nice 4 kpc distance check, is only about 6.5 million years.
Ah.
And that's reasonably close to the age inferred for the other binary, W13, by Beezer et al., which was less than 5 million years.
So you really do have different groups of stars within the same cluster, all confirmed to be at the same distance now, around 4 kpc, but pointing to significantly different ages spanning from maybe less than 5 up to almost 12 million years.
That's exactly the conclusion. Both the Navarrete et al. Study and the Beezer et al. Study, looking at the EDR3 data, conclude that the observations are best explained not by a single formation burst 5 million years ago, but by a period of star formation that occurred over several million years. It likely started perhaps around 12 million years ago, forming the stars that are now red supergiants, and continued until maybe 5 million years ago, forming the stars we see in systems like W13 and W36.
A formation period lasting maybe 5 to 7 million years itself.
Something like that, yes.
I mean,
Potentially spanning that whole 5 to 12 million year ago range.
and are theoretical models catching up to this more complex picture of extended star formation in massive clusters?
Broadly, yes. The source material mentions recent models by Yusuf et al. In 2022 that include complexities like the effects of stellar rotation, which can alter lifetimes. These newer models are starting to be able to reproduce the observed populations of red supergiants, yellow hypergiants, and Wolf-Rayet stars coexisting across that kind of age range.
But it's still challenging.
Oh, definitely. It's challenging for the models to get all the details right, especially regarding exactly how these massive stars lose mass through winds or how they interact in binary systems, which can significantly alter their evolution. So further refinement of the models is still needed. But the general idea of a prolonged formation period seems to fit the diverse population of Westerlund 1 much better than a single instantaneous burst.
It's pretty remarkable when you think about the journey, isn't it? 25 years ago, the Hipparcos satellite couldn't see any stars clearly enough in Westerlund 1 to measure parallax. Now, just the first 34 months of data from Gaia EDR3 have fundamentally changed our understanding of this massive cluster, pinning down its distance to 4 kpc and revealing this complex, extended birth.
It really highlights the transformative power of precise astrometry from space. Being able to measure those tiny parallax shifts and the precise, proper motions, how the stars move together across the sky for these relatively distant, dust-obscured stars was absolutely the key that unlocked the door. It's given us a view into its distance, its age spread, and even its 3D structure that was simply impossible before Gaia.
And with future Gaia data releases coming, presumably with even better precision, better handling of systematic errors, and more information on binary stars, what's next for unlocking more secrets of Westerlund 1?
Future Gaia catalogs, like DR4 and beyond, will undoubtedly bring even deeper insights. They'll allow for even more accurate membership selection, filtering out non-members even better. This will lead to tighter constraints on the cluster's average distance and internal structure. We might even start to resolve the finer details of its internal dynamics, how the stars are moving within the cluster, revealing more about its formation process and how it's evolving dynamically over time. And better data on binaries will be crucial for refining those age constraints.
So we've traveled quite a path in this deep dive. From a cluster initially thought to be maybe closer, but definitely formed in a single neat burst, through a period of confusing and conflicting distance data from early Gaia releases, to now a strong consensus around a distance of about 4 kiloparsecs.
Right.
And crucially, this precise distance data, when combined with other observations like photometry and spectroscopy, especially of those evolved stars and binaries, has revealed a much more complex and interesting history star formation that likely unfolded over several million years, not instantaneously.
It's a perfect example, really, of how precise astrometry from missions like Gaia acts as a cornerstone. When you combine it with other astronomical tools measuring brightness in different colors, measuring spectra to get chemistry and velocity, it becomes incredibly powerful. It's absolutely essential for resolving these long-standing puzzles, not just about individual objects like Westerlund 1, but about fundamental processes like how massive stars live and die, and how these huge star clusters, the building blocks of galaxies, actually form and evolve over time.
Thinking about this incredible collection of massive evolved stars, the supergiants, the Wolf-Rayets, the hypergiants, that weird pulsar, all packed into that small volume, and now understanding they formed over millions of years. What might the future hold for Westerlund 1 itself? As these stars continue their dramatic life cycles, some likely ending as supernovae, leaving behind black holes and neutron stars, could they significantly impact their surroundings? Maybe interact with those foreground stars near the Scutum Crux arm, or the cluster's own halo population that Gaia is revealing?
That's a great question to ponder. I mean, you have Dozens, maybe hundreds of massive stars destined to explode over the next few million years in a relatively small volume. The cumulative effect of those supernovae, the energy, the heavy elements ejected, must have a profound impact on the remaining gas within the cluster, and perhaps even blow gas out into the surrounding interstellar medium.
Could it trigger new star formation nearby? Or just disrupt things?
Possibly both. And you have to wonder about interactions. Could a supernova remnant expanding outwards interact with that foreground population Negra identified near 2 kbc? Or could stars ejected from Westerlund 1 through dynamical interactions travel out into its halo or beyond? These are the kinds of questions that future observations, perhaps linking Gaia data with surveys like the James Webb Space Telescope looking deeper in the infrared, might start to address. What secrets might the next generation of astronomical data reveal about the ultimate fate of this dynamic, complex cosmic city? It's still got a lot to tell us.